Dear students, today we are discuss about the mechanical property of solids, elasticity chapter. In this chapter, in the second lesson, we discuss about Poisson's ratio, stress strain curve, potential energy in a stretched wire, and stress, thermal stress. Thermal stress and strains we want to discuss today. Now, first we want to discuss about the Poisson's ratio. What is meant by the Poisson's ratio? We want to know. Here, for example, a wire is stretched from a fixed support and we apply a external force or deformation force like this. The length of the wire is say L. What happens? The length of the wire get increased, but the diameter of the wire decreases. It becomes thinner when it's stretched. That means it is a lateral contraction strain. It is lateral contraction strain. Here it is delta L, increase in length, elongation strain or longitudinal strain. Here, for example, the diameter or radius of the wire is delta R, and delta R is the decrease in diameter. Then we define the Poisson's ratio. Lateral contraction strain by longitudinal strain. Longitudinal strain. It is defined as the ratio of lateral contraction strain to the longitudinal strain within the elastic limit. It happens within the elastic limit. Now we write it as minus delta. This is the decrease in the radius by R, radius, original radius of the wire. Delta L by L. It is increase in length by original length. This is the Poisson's ratio. For example, if its value changes from -1 to +1. These are the theoretical limits of Poisson's ratio, and practical limits are 0 to +½ 0 to +½ The limits of theoretical limits of this sigma, that means Poisson's ratio is equal to lies between -1 to +½ practical limits. These are the theoretical limits. These are the practical limits. Practical limits of Poisson's ratio. Here minus sign comes due to decrease in radius of the wire. This is about the Poisson's ratio. Now we want to discuss about the behavior of wire under gradually increasing load or a stress strain curve in a stretched wire. For example, a wire is taken, a load is gradually increased on it. The behavior of wire we studied here. We take strain on the x-axis and the strain on y-axis, stress on y-axis, strain on x-axis and stress on y-axis. For example, within the up to certain extent, if you increase the load, stress is directly proportional to strain. It is known as P. It is O, origin is taken as O. Up to certain limit, stress is directly proportional to strain. Now if we increase further, load further on the wire, what happens? It behaves like this. The curve gets like this. It is known as E, elastic limit. If you remove the load from the wire, it regains its original condition. If is further increased. This is known as elastic limit. Further increase, it increases and finally the curve becomes like this and finally it breaks. This is known as breaking point. Breaking point. If the distance between these two, breaking point and elastic limit, is greater, then the metals are called ductile materials. Ductile materials like copper, gold and aluminum. Those type of metals are called ductile. If the distance between elastic limit and breaking point is large, then we call it as ductile materials. Now, if the distance is less, the distance between elastic limit and breaking point is less, then the materials are called brittle metals, like glass. Brittle metals like glass. That means after elastic limit, if the distance is less, after elastic limit, they break at a very near point. That means it does not show any property or any property of elasticity, and also it breaks at a small increase in load. This is about the stress strain curve. For example, if further increase, for example, we take another point, for example, up to this point, we take a load is further increases from after elastic limit. If you remove this one load, remove this load, what happens? It does not follow this one, this path. It follows this path. It is known as, for example, X, I say. It is E, permanent increase in length is taken place here, X. The OX is the permanent increase in length. That means it does not show any elastic property. There is a permanent increase in length. After that, this point, behind this point, it becomes thinner and thinner. That means the solid behaves like a fluid and becomes thinner and thinner and finally breaks at D. This is known as wheeling point. Wheeling point. That means the point from which wheeling starts is called wheeling point. Now this is about the stress and strain curve in a stretched wire. If we take a wire and load is gradually increases, what happens? Up to certain load or stress, these two are directly, stress and strain are directly proportional. This point up to which these two are directly proportional, that point on the graph is known as proportionality limit. Now we further increase the load, what happens? It goes to E. If you remove the load from the wire, it regains its original condition, it follows the same curve and retraces the same curve. And this point is called elastic limit. Elastic limit. Elastic limit. Further, if you increase the load, what happens? At this point Y, the wheeling of a wire starts, that is known as wheel point. Further, if you increase the further, sometimes without increase in load, it breaks at B. The point B is known as breaking point. The stress corresponding to breaking point is known as breaking stress. Breaking stress. If the distance between E and B is large, then they are called ductile materials. If the distance between these two is less, then they are called brittle metals. Ductile metals. Ductile metals are used to make sheets and wires. These are not, in this case, this is not, in case of brittle metals, it is not possible to make sheets and wires. Then those materials are called brittle metals. This is about the stress and strain curve. This OX or E is known as the permanent set. That means there is a permanent increase in length behind the elastic limit. This is about the stress and strain curve. Next one is potential energy of a stretched wire. Potential energy of a stretched wire. What is meant by the potential energy of a stretched wire? For example, if you take a wire and it is stretched by using a external force, what happens? There is increase in length. That means we must do some work against these restoring forces in the wire, present in the wire. That work done is stored as potential energy in the wire. That means the energy possessed by a stretched wire, or the wire is in strained condition, it possesses the potential energy. That means we must do some work to elongate this wire or the stretch this wire. This work done is stored as elastic potential energy inside the wire. That is calculated, for example, if we consider similar to the spring, energy is equal to, potential energy is equal to half K into delta L into delta x whole square. Delta x whole square, that means it is delta L, it is the length of the wire, area of cross section is A, I say, Young's modulus of the wire is Y, I say. Then here half K means Ya by L. It is similar to the spring. The spring constant of the wire is Ya by L. Y is the Young's modulus, A is the area of cross section, L is the length of the wire. And delta x or delta L whole square here. Now we write it as like this. We rearrange the terms like this. Delta L by L, strain, delta L by L, strain. Next, Y into delta L by of Young's modulus F L by A into delta L. Now we can write it as Ya delta L, Ya delta L of K as like this U. Then we write it as like this. Potential energy per unit volume, half delta L by L into Ya delta L by AL. A cancel. From this we write it as F by A by L. That means Y delta L by L means stress, half into delta L by L into Y delta L by L. This can be written as half strain into Y into strain. That means half stress into strain. This is known as potential energy stored for unit volume. It is the energy stored, total potential energy stored in the wire. It is potential energy stored for unit volume of the wire. This is about the potential energy stored in a stretched wire. What you taken for example, we take a wire on which we apply a force F. There is extension delta L. The initial length of the wire is L. Y is the Young's modulus of the wire. Now we use the formula potential energy of a spring similar to this one. That is why we use that formula. U is equal to half kx square or k delta x square. This means delta L means delta x means delta L here whole square. Here spring constant of a wire is known as Ya by L. Young's modulus area of cross section by A. Now we substitute that one. We get after simplification we get half stress into strain. Next one, thermal stresses. For example, a rod is fixed, if a rod is fixed between two rigid supports and then heat or cooled, what happens? A thermal, for example, if we heated this rod uniformly, what happened? It presses this wall or rigid supports like this. That is why a restoring force is developed like this. Restoring force is developed like this. It gets compressed. That is why restoring force is developed in opposite to the force applied by the rod on the walls or the fixed supports. Now, y is the Young's modulus of the rod, length of the rod is L, A is the area of cross section, the increase in temperature is delta T, the coefficient of linear expansion of a rod, temperature coefficient of linear expansion of a rod is alpha, then increase in length of a rod, L alpha delta T. Now, we write it as delta L by del L is equal to alpha delta. It is the thermal stress. Thermal strain. It is thermal strain. Now we write it as F, thermal force. F is equal to Ya delta L by L. That means Y is equal to FL by A into delta. From this formula we can write like this. From this right into delta L by L. This is the thermal strain. We put here A alpha delta T it becomes. This is the thermal force applied by the rod on the walls or fixed supports. Now F by A is equal to Y alpha delta T. This is known as thermal stress. Ya alpha delta T. Y is the X modulus of the Y, A is the area of Y alpha delta T. L is, alpha is the coefficient of linear expansion of the rod and delta T is the rise in temperature. Young's modulus. Y is the Young's modulus of the Y. Okay.